Hello everyone, my name is Abdurrahman Khalil. I am with the Department of Mechanical Engineering, Memorial University, Newfoundland, Canada. My talk today is about health monitoring of mixed autonomous and human-driven vehicle platoon using transmissibility identification. My co-authors are Muhammad Al-Junaida, Khalid Al-Junaida, and Deepak Kondor. I will start today with the problem formulation, then I will model an autonomous and human-driven vehicle platoon. Then I will define transmissibilities and how can we identify transmissibilities. Then I will introduce some possible and common fault models in the mixed autonomous and the human-driven vehicle platoon. After that, I will introduce the transmissibility-based sliding mode control, which is used for fault mitigation. And then I will present some simulation and experimental results. Consider first this mixed autonomous and human-driven vehicle platoon. This platoon can be represented within this nonlinear state space representation, where F here represents the human effect of the human-driven vehicle. F here is considered to be unknown. We will start first by splitting this platoon into two subsystems, where the first system is the autonomous vehicles and the second subsystem is the human-driven vehicle. Now we will rearrange the state space representation and consider F here as an independent excitation signal on the platoon. So after rearranging both of the desired velocity of the whole platoon and the human effect as U, we will end up with this linear state space representation of the platoon. We will start first by modeling the CAV vehicles, the autonomous vehicles. This model for the autonomous vehicles is taken from Rajesh Rajmani book, Vehicle Dynamics and Control. This model considers first a lag filter between the desired acceleration and the actual acceleration of the autonomous vehicle, where P here represents the time differentiation operator. The reason behind considering P instead of S is to count for non-zero initial conditions within this transfer function. Then by integrating this transfer function, we get the relation between the desired acceleration and the vehicle velocity. After that, we consider the cruise control of the vehicle as a PI controller. Then we will end up with the closed loop vehicle model as it's shown here. Next, we will model the human-driven vehicle. Again, F here is considered to be unknown. So we will adopt first the IDM model for the human-driven vehicle, where here we could see that F is a super nonlinear function. So according to the literature, the vehicle that follows the human-driven vehicle is supposed to receive the kinematic information about the vehicle that is in front of the human-driven vehicle through a vehicle-to-vehicle communication link. Furthermore, the vehicle that follows the human-driven vehicle here is supposed to measure the velocity of the human-driven vehicle through the perception sensors. So thus, the block diagram of this portion of the platoon that represents the interaction between the human-driven and the autonomous vehicles. The desired velocity of the vehicle that follows the human-driven vehicle is supposed to be the average of the human-driven vehicle and the vehicle in front of it. This is in case that this vehicle moves slower than the human-driven vehicle. If it travels faster, then we assume that it follows only the velocity of the human-driven vehicle itself. Now let's start with the transmissibility definition. Consider this platoon with only two vehicles, and as we described before, let's assume the desired velocity of the platoon and the nonlinear effect of the human-driven vehicle as independent excitations on this platoon. And we have here y1 and y2 as two measurements. So the goal of this paper is to obtain the response of a subset of sensors based on the response of the remaining sensors, as we can see here. So this T here is called the transmissibility operator from y1 to y2. Now, assume we have a platoon of n vehicles, where vehicle J is faulty. We will first, this platoon is with unknown desired velocity, unknown dynamics, and with only known velocities. Then we will split the platoon velocities into two subsets of velocities, while yi here represents the healthy measurements of the platoon that is considered from vehicle 1 to vehicle J, and then from vehicle J to the end of the platoon are considered to be corrupted because of the fault in vehicle J. Then we can obtain our transmissibilities using these formulas. For clarification purposes, assume we have a simple case where yi and yo can be represented within these transfer functions. Then by dividing yo over yi, we will obtain our transmissibilities as no over ni, where no and ni are the numerators of the first two transfer functions. Note here, the final transmissibility operator is independent on the excitation signal or the desired velocity of the platoon V1 star. So we consider here to identify transmissibilities a non-causal impulse, finite impulse response model. So the FIR models are simple model structure. They can characterize complex linear models and can be used for online applications. Moreover, these models can capture the unknown dynamic models. They also can capture the unknown model orders, and it's easy to identify. To identify it, let's consider theta here as a vector of the model parameters. Then a parametric least squares identification can be obtained from the sensor measurements. And after that, we can obtain the velocity the velocity estimation of the platoon using yi multiplied by t, the transmissibility operator. We can obtain the prediction of yo. After that, we can obtain our fault detection residual as the difference between the measured velocities and the predicted velocities. To model these faults, we first model the perception sensor fault, which is a fault of the vehicle that follows the human-driven vehicle. So we model this fault as a bounded noise signal added to the measurements of VI, H. The second fault is the false data injection in the communication link between the vehicle that is in front of the human-driven vehicle and the vehicle that follows the human-driven vehicle. And the third fault is a communication time delay in this communication link. And again, we have unknown dynamics, we have unknown desired velocities, and we have unknown faults. As an example, consider these two platoons, where one is fully autonomous and one with a human-driven vehicle. So here we can see the responses of both the platoons. We can notice here with the human-driven vehicle that the response of the human-driven vehicle is much slower than the autonomous one. Then consider faults here in the vehicle that follows the human-driven vehicle and vehicle 4 in the first case. And here we present the error in both cases within these faults. We can notice here how the error would increase significantly where there is a human effect within this platoon. To mitigate these faults, we consider the transmissibility-based sliding mode control. So this sliding mode control is based on the transmissibility prediction instead of the observer estimations. So consider this platoon first. Then we take the desired velocity of vehicle J, the faulty vehicle, to the transmissibility operators for fault detection. So if it detects a fault, then we will switch to the sliding mode controller control signal theta here. Next, we consider simulating this platoon with 5 vehicles where vehicle 3 is a human-driven. We set the desired velocity of this platoon to bounded unknown signal, and we consider all faults in vehicle 4. This figure here shows the residual and the control signal for the 3 fault scenarios where each fault is introduced separately. This figure here shows the velocity of the vehicle 4, and this figure shows the norm of residual over a sliding window, where we can see that after almost time 60, the norm of residual it dropped below the threshold limit for these 3 faults. Similar results can be obtained experimentally. We consider this setup with the 3 autonomous robots, where the second robot is controlled by a human. This figure shows the residual and the control signal. And similarly, this figure shows the velocity of the third robot, and this figure here shows the norm of residual over a sliding window, where we can see almost at time 60 the norm of residual it dropped below the threshold limit for these 3 faults. To conclude, we proposed firstly transmissibility operators to detect and mitigate faults in a mixed autonomous and a human-driven vehicle. Our technique uses only available sensor measurements and is completely independent on the desired velocity of the platoon, the human-driven effect, and the platoon dynamics. The faults was mitigated based on the sliding mode controller that is based on the transmissibility operators. And as we saw, this technique was used successfully in simulations and in experiment results. Thank you.